In this video, we're going to talk about what a Fourier series is. So some background for this first. So in calculus, you would have likely seen how to express functions as infinite series using what's called a Taylor series. So just as a brief review, what we did there was we had a function f of x, and we tried to express it as an infinite polynomial. So I'm going to write that as c naught plus c1 times x minus a plus c2 times x minus a squared. So we're starting to get some polynomial terms, plus dot dot dot, plus cn times x minus a to the n, and then plus dot dot dot. So this is an infinite polynomial. Infinite polynomial. Or sometimes called the Taylor series. So in calculus, you would have seen that the coefficients of this Taylor series, of this infinite polynomial, were given by Cn equals the nth derivative of f evaluated at a. So a here is a constant. And then all the c's are constants, divided by n factorial. And for special functions, for certain functions, the approximately equal to becomes exactly equal to. So more formally, we say that there are some functions for which this series converges to that function. So there are several applications of these infinite polynomial expressions for a function. So I want to list a few of them for you. So the first is calculators actually use these Taylor series, these infinite polynomials. They use them to figure out what something like sine of 1.4 is. So 1.4 is not a nice angle. Like we can't figure out what sine of 1.4 is in the same way we can figure out what sine of 30 degrees is or sine of pi over 4 is. A calculator actually determines something like this by using the Taylor series, this infinite polynomial for sine of x, and then using that to approximate what sine of 1.4 is. So we also use these infinite polynomials to approximate solutions to differential equations that can't be solved by hand super easily. So I've listed one example here, y double prime plus t squared times y prime equals e to the t. These infinite polynomials can also show up in other fields like physics. For example, using the energy function within physics, they can show up. And then maybe the most important application is Euler's formula. So to show Euler's formula, one of the ways to prove Euler's formula is to use these infinite series. And this formula is really foundational to the entire study of complex analysis. Okay, so in differential equations, we're going to express a function as an infinite series in another way. So in differential equations, we are going to have a function, and we are going to try to approximate it in the following form. So we'll have a constant term in the front, which I'll call a naught over 2, and we'll see why later in a future video. And then we're going to have a series of sine and cosine terms. So I'm going to write this series in sigma notation. So I'll have n equals 1 to infinity, and then I'll have a sub n times some cosine term, and I'll state what's inside of this cosine term later, and then plus bn times some sine term, and again I'll write down what's inside the sine term a bit later, but for right now that's not super important. Okay, so the key thing about this is what we're going to be trying to do is we're going to be trying to write this as an infinite, we're going to be trying to write our function as an infinite sum of sines and cosines. When we do that, when we write our function f of x in this way, or when we try to approximate it in this way, this thing on the right-hand side is called the Fourier series for f of x. So for special functions f, this approximately equal to becomes an equal sign. In other words, we say that the Fourier series will converge to that function f of x. So what are some applications of Fourier series? So the most immediately relevant to us is they let us solve classic partial differential equations. So that's what PDE stands for, partial differential equations. So in the textbook, these show up in sections 9.5, 9.6, and 9.7. So for example, the heat equation shows up in section 9.5, and the wave equation shows up in section 9.6. These are classic partial differential equations that can be solved with the help of Fourier series. So some other applications of this are the fields of harmonic analysis, signal processing, image processing. They also show up in forensics, and there are many, many others. All right, so now I want to talk about the key idea and sort of tie everything together. All right, so here is the idea. We're going to be looking at some set f. So I've written this f as like a script f. That's why it looks all curvy. So this set f is a vector space that consists of piecewise continuous functions on an interval that goes from negative L to L. So L is some positive number here. So this vector space, that contains all these piecewise continuous functions is infinite dimensional. Okay, and so what I mean by piecewise continuous is that our functions are continuous, except possibly they could have finitely many jump discontinuities. So for example, let me just draw a basic graph here. So for example, if I had a graph that had a jump discontinuity, so let's say maybe it started here at a closed point, and then there's an open circle, and then it jumps down and does something like this, that would be piecewise continuous. It was continuous everywhere, except it had one jump. So if a function like this is allowed to have finitely many jump discontinuities. Okay, so this vector space is infinite dimensional. So what we are going to try to do is we're going to try to construct an orthogonal basis for this vector space, for script f. And we're going to do that using sines and cosines. And to impose orthogonality on this vector space, we're going to use inner products. So the inner product we're going to use is, so the inner product of f and g is going to be the integral. In this case, I'll integrate from, so let's just say from a to b. Later we'll be a little bit more specific. We'll end up integrating from negative L to L. That'll be our interval. So right now I'm just going to write down the general formula for this inner product. So f of x times g of x. So we're going to use this inner product to define our notion of orthogonality here. And we've seen this inner product before. Okay, so it turns out that when we do this, almost any function f is a linear combination, an infinite linear combination of sines and cosines. Okay, so that brings us to our key goal. Our goal is going to be to try to express f of x in the following form: a naught over 2 plus this infinite series that consists of cosine and sine functions. So now I've written down what's going to be inside the cosine functions and what's inside the sine functions. It's going to look like n pi x over L. So inside the cosine and inside the sine. And specifically what our goal will be is to figure out what these coefficients are. So what are these a_n's and what are these b_n's? So we'll start to talk about that more, like what are formulas for a_n, b_n in the following video.